Hello everyone, I'm Sascha von Meier and I'm here to talk about phasor-based control, which is a new strategy we've developed to help coordinate diverse, distributed, and renewable resources. In the big picture, what we're trying to do is to help the integration of renewable intermittent power generation, storage, new electric loads such as electric vehicle chargers or other electric loads as we're phasing out natural gas and electrifying end uses. That's going to add to the electric demand throughout distribution systems. And we want to facilitate the integration so that we're not limited by feeder hosting capacities for added solar or added load. We can avoid expensive upgrades of the distribution system by intelligently coordinating those diverse and controllable resources. For them to be good citizens on the grid, that is, to do the right thing at the right time, they really just need the right information that they can act upon. And phasor-based control is one very novel strategy for doing that using direct physical measurements from the grid. So I will tell you about a project with many interdisciplinary team members funded by the US Department of Energy to develop phasor-based control. It's part of the Solar Energy Technology Office's Energize program. This was finished in 2020. Project partners include Lawrence Berkeley Lab, University of Michigan, Opal RT, Ping Things, GridBright, and PG&E. The basic idea is that we have a layered control paradigm in which a supervisory controller decides on the big picture, decides on the desired operating state, and local controllers will recruit resources to actuate and help achieve the target values prescribed by the supervisory controller. The entire power flow situation here is articulated in terms of voltage phasors. So those would be voltage magnitudes, V, and angles, delta. So that refers to the precise timing of the voltage waveform. And together, the voltage phasors at each node in an AC network define everything there is to know about power flow. They will define real and reactive power flow. So in phasor-based control, this is a very precise way to formulate what is the power flow condition that we would like to see, and the supervisory controller can take all kinds of input information from economics, from weather forecasts, incorporate that into an optimization. We're agnostic here to the criteria, but it will compute target voltage phasors for every point on the network. And the local controllers will then talk to the solar inverters, the controllable loads, the batteries, and recruit them to turn up or down depending on what's needed to maintain the desired power flow profile in terms of those phasors. So in this case, the substation transformer here would be the reference point. We always need a reference point to describe a phasor difference that then corresponds to power flow. This can be scaled up to the transmission level where you would have different locations in the transmission network. But in our project, we started out developing and testing this framework for individual distribution circuits. It might be more intuitive to think about recruiting resources on the basis of pricing. Now, price-based control has the caveat that it's a lot of computation to do, and it's very tricky to calculate different prices for different moments in time and different specific locations with enough granularity to really achieve what we want, which is to alleviate any constraints on the grid to make sure that we prevent violations that might include power flow violations, thermal limits, voltage limits. So to be meaningful in the distribution system context, prices would really have to be very, very granular. And the real-time price for electricity between you and your neighbor might not be the same. It might not be the same across all phases, A, B, and C, on your street. So that gets pretty complicated to imagine how you would achieve really specific local recruitment of resources. If you had to compute a price for everything, you'd have to know your model, your circuit model very accurately. And then you also have another source of uncertainty, which is how would actual devices or humans respond to prices? So instead of going from physics to economics and back to physics, what we do in phasor-based control is for the fast response, we stay in the realm of physics. We measure the physical state of the electric grid, which we can do globally as well as locally, communicate that directly to devices to make control decisions to respond to the physical needs of the grid. And they can do that on the scale of seconds. And then on a longer time scale, we worry about the economics and figure out, well, okay, how much money needs to change hands in order to compensate the devices for doing that. So the perspective here is much more akin to ancillary services on the grid, where a generator would just be there and do what it takes in response, for example, like doing frequency regulation services or reactive power volt-var control. In a sense, phasor-based control is very much like managing voltage, but it's extended to not just reactive power, but also real power by using both voltage magnitude and angle. So the basic idea here is let's have fast-acting response to the needs of the grid, keep that in the realm of physics, and then on a slower time step, it could take minutes rather than seconds. We worry about the settlement, and we worry about optimization and paying everyone their money. This is a paradigm that really prioritizes reliability and disturbance rejection and stability. A really important enabling technology is Power Standards Lab micro-PMU, which we developed together on an ARPA-E project. That now makes it possible to measure voltage magnitudes and phase angles with the kind of precision that you would need to actually base control decisions on that in the distribution context. So here's an illustration of the voltage phase angle being a time shift in units of degrees, where 360 degrees is one complete cycle. And that voltage phase angle physically helps drive power through a transmission or distribution line. Here's an illustration of some measured voltage phase angle differences. In this case, it's the difference in the timing between the voltage at micro-PMU 1 and 2 when there's power being generated by that large solar PV plant. And you can see that we're talking about less than 1 degree of angle. So that's less than 1/360th of a 60th of a second. But that voltage phase angle difference between the two PMUs corresponds fairly closely to the power injected here by the PV site. It doesn't correspond exactly because there's also load here from the rest of the circuit that's not captured in this blue diagram. But the important takeaway here is the precision that's needed, and without really fine-grained, precise voltage phasor measurements, you couldn't imagine even doing phasor-based control at this scale. Now, at the transmission level, voltage phase angle differences are much bigger because we're talking about long distances and more impedance on the transmission lines. So this heat map, if you will, shows you that power is flowing from red to blue because the voltage phase angle is tens of degrees ahead of or more positive in these red regions compared to the blue and purple regions. In fact, this wouldn't even be stable if it were just a single transmission line, but there are many, many substations and generators, of course, across the whole eastern US that keep this whole system synchronized. The takeaway here is that this heat map or profile of angles corresponds to the real power flow. And what we'd like to do is represent the desired power flow in terms of the voltage phasors at each point along the network, and then communicate that to the resources to help maintain that. And if all the resources participated and maintained exactly the desired phasors, you would then have a state of equilibrium where the frequency would stay constant and you would no longer have to do frequency regulation. But starting slow, we can sort of adopt this phasor-based control from the individual distribution feeder to begin to help support and stabilize the whole grid. Let's look at why the voltage phasor is a useful variable, and in some sense more useful than just explicit real and reactive power or P and Q measurements for which you would have to measure the current. Our objective here is for this resource, resource number 1, to counteract whatever crazy things its neighbors are doing. So those might be volatile loads, they might be uncontrolled solar generation with passing clouds, power going up and down, driving the voltage up and down. So all these kinds of volatilities we want to counteract. Suppose we have a battery resource here that can be either charging or discharging in response to what this circuit needs in order to stabilize its overall power demand. So you could imagine doing that by just measuring the current at the feeder head and saying, well, let's keep these numbers P and Q for the whole circuit as constant as we can. That's doable. What you lose in doing so is the locational information, because in fact, if you're worried about the voltage profile along the circuit, which will drag the voltage down if there's too much load at the end, or it will push the voltage up too far if there's too much generation at the end, you will see that in the voltage phasor profile. You would lose that by measuring just P and Q. You wouldn't know, well, where is the extra load happening? If it's close to the substation, maybe we don't care. If it's at the feeder end, maybe we care a lot and we need to counteract that more aggressively. So by looking at the voltage phasor at a particular location, we're getting a really useful indication of how much strain or stress there is on the circuit and how close it is to maybe overloading, or whether we are within the bounds of voltage that we want to manage there. At the same time, we're getting that locational information without having to compromise our neighbor's privacy. So we don't need to measure the branch currents at any of our neighbors in order to know approximately, sort of from a geographic standpoint, where is this load occurring, and where can we best compensate for it. So we're getting the actionable information about how are these loads or generators affecting the grid without snooping around in their private data, right? All we need to measure is a nodal voltage in order to see how the neighborhood is being affected. Now, this is in a sense similar to what's already done for volt-var control, for reactive power management, adjusting to real-time measurements of the voltage and correcting the voltage magnitude by increasing or decreasing reactive power output at the inverter. In phasor-based control, we augment that, or integrate it with real power control so that we have this whole integrated control schema for both voltage, magnitude, and angle, and both real and reactive power. Because there are some inefficient operating conditions that could come about if you're using too much reactive power, maybe to address a higher or low voltage magnitude, and you can recruit more effectively real and reactive power together to get the power flow situation that you want. So we can co-optimize. Another example here to build intuition is the case at the transmission level, where the phasor-based control allows resources to respond directly to contingency events, such as losing a transmission line. In this example, we imagine two identical parallel transmission lines, and one of them suddenly drops out. For whatever reason, we don't know. All we know is that, well, the impedance is going to double. The impedance of this path effectively is going to double. The consequence, before any other control actions have been taken, is that this phasor difference, V1 minus V2, will jump up instantaneously because there is now a bigger impedance, and there will be the attempt to transfer the same amount of power. It won't actually come out to be exactly the same amount of power because some of it will sort of rearrange itself in the network. But just looking at this local situation, we may be in some trouble because this transmission line, if the other transmission line didn't immediately trip, which we'll assume it didn't if the system was previously in a secure state, but it may be operating on an emergency rating. And so we want to get it back, restore it to the original operating condition, or at least restore it to a safe condition as quickly as possible. So with phasor-based control, the resource at bus 2 here will observe the step change, and without having to wait for any further information or any further instruction, it will know that it needs to step up its generation or step down its load as this phasor difference suddenly increases. So it will help avert some cascading failures, for example. If we're concerned that this other transmission line, the remaining one, may now trip offline because the first one tripped. So we will help restore the original condition, which we knew to be safe and within the specs. Because by trying to restore the phasor difference between V1 and V2, we're basically going to try to restore the previous power flow on just the one transmission line, meaning we're cutting the whole power flow in half. Now, that may not be quite possible to achieve, but at least the resource will instantly have the information about which direction it should be acting in, increase or decrease power. And it buys us time. It may not be economical for the resource at this location to be bending over backwards to produce so much more power to drive this phasor difference back, but after a few seconds or even minutes, the supervisory controller can take charge of the situation, can re-optimize the situation based on more detailed information about what just happened, and can reallocate or redispatch. So re-optimize the power flow, and then it will issue a new target for bus 2, having taken into account all the available information. Until that re-optimization, the resources will know the right thing to do in order to stabilize the system and prevent an outage from occurring because disturbances have cascading effects. So it's the phasor profile that instantly reveals the stress on the transmission path, and that will give us a physically sound basis for making control decisions while we wait for the economic optimization to be done. Now, in our project, we did a lot of simulation, starting with small distribution circuits, like this IEEE 13-node feeder. That's very well understood, it's straightforward, so we could play with it. And in this case, we had a control objective where we wanted to basically hold constant the power flow across the transformer, which means hold constant the phasor difference between the substation bus 650 and this bus or node 637. And in this example, we're recruiting assets from several different places on this distribution circuit. These are all different actuators. They could be solar or battery inverters. They could be controllable loads. So a local controller is calling upon its local resources to work together and drive this target, drive the voltage phasor to the target value here at node 632. That's just one example of a use case, that is to control net power flow, real and reactive, at the feeder head. We're agnostic here to what optimization criteria we want to choose. We may want to balance the three phases. If, for example, a lot of solar is connected on phase A and not so much B and C, we may want to tell the inverters at phase A to do something different than inverters on phase B and C, or loads on the three phases. We may just want to manage voltage volatility and keep the voltage magnitude within the range. But another interesting use case would be to drive the phasor to a particular value at a point that's on one side of an open switch between this circuit and another neighboring circuit or circuit section. Because when you're about to close a physical switch, you want to make sure that the voltages on the two sides are not too different. Otherwise, you get a big arc across the switch. And sometimes in real life, utilities would actually bring a diesel genset out to location to help drive the phasors to make them compatible to be able to close a switch without previously having to de-energize everything. Phasor-based control is one way to recruit all the existing resources to do exactly that. You just issue a new phasor target, and you have to measure at that location to say, let's everybody drive the phasor to a certain value here. Finally, a promising, I think, economically viable use case for phasor-based control is to look at the benefit to the transmission system of having net power flow control at the feeder head for multiple distribution circuits, and to look at what that can save you in terms of secure operations. A transmission level dispatch that might not be considered N-1 secure, that is, you couldn't do it because if any one item fails, the lights would go out. If you have phasor-based control in place, that operating state may be acceptable, may become secure, because you can be confident that the distributed resources from behind these substations will respond to a change in the grid operating state. So without going too much farther into these different possible use cases, let's look at just how we've simulated this. And we used Opal RT's ePhasor Sim for basically checking out, can we make this work? We simulated many, many different scenarios. Essentially, our goal here was to reject disturbances on a timescale shorter than 1 second, which we're able to do. We developed 3 different local phasor-based control algorithms, and I'll come back to that. Just briefly here, what we're looking at in the graphs is we're looking at voltage magnitude and angle at the performance node. In this case, that was at node 632. And we've simulated some really big disturbances. The 3 colors are the 3 phases. And what we're seeing is that with actuation from the resources, both real power P and reactive power Q, in units of per unit in this case, which would be many kilowatts, but with that actuation, we're restoring the voltage magnitude to its desired value here, and we're restoring the voltage phase angle to its desired value. Now, to do that, it helps if you have model information about the distribution system that you're on. If you have a good distribution circuit model, you can design a multiple input, multiple output, or MIMO controller. In this case, our linear quadratic regulator that takes all of the information into account and does actuation very quickly. However, we don't often have a really trustworthy, reliable distribution system model. So we have to assume that our local phasor-based controller is essentially having to figure this out on the fly. It's going to have to tune its control gains to the physical situation that's actually there. Or something may have changed in the network since we last looked at our model. So a straightforward proportional integral, or PI controller, is what's shown here, and it can produce these results. There's also a more sophisticated retrospective cost adaptive controller that was developed by University of Michigan, which is fine-tuning itself by looking at its history of how it could have made better control decisions and looking at outcomes. The upshot here is that we have 3 different algorithms, all of which can be made to work, and we don't depend on having a reliable distribution circuit model. Just a few words here about scaling. So we're sort of operating in this blue realm here where the supervisory controller is just calculating power flow for one circuit, and the local controller is recruiting actuators to respond to that. This paradigm can be scaled up almost in a fractal sort of way, where there can be multiple levels of supervisory control at the transmission scale. And in a sense, this controller acts as a local controller looking upward, facing upward into the transmission network. So you could ultimately specify a designed phasor for every node in a large network. And you can distribute out the control responsibility so that local groups of controllers and resources, actuators, each have sort of a zone that they're responsible for. We tested out phasor-based control at the Lawrence Berkeley Lab and the Flex Grid. So we have 3 inverters here that are being driven. We also have load banks, so these are mainly variable frequency drives. Those will respond only to real power commands, not reactive power, but that would be typical of a lot of loads that you're trying to control. Here we have the Opal RT simulator, which is basically simulating an entire distribution circuit, and we're putting these physical resources, we're placing them at one node of that circuit and pretending that they're interacting with the whole rest of the circuit. There's also 3 batteries in the back. You can see them back here. And there's Maxime. Hello, Maxime. Working with, looking at the 3 micro PMUs that are monitoring phasors at the different locations in the network that we're simulating. So it's integrating this hardware, putting the hardware in the loop with the in silico simulations. Communication is a really important piece of this. And we're using here the wave message bus developed at UC Berkeley, which is a secure way to basically bring different actors together to cooperate in maintaining this steady state in the grid without revealing private information that they don't want to have revealed. So it's a publish-subscribe message bus where every entity that publishes information to it can specify who's authorized to read that. And the one stream of data that everybody's going to want to subscribe to is a reference PMU. So for our distribution circuit, it might be the PMU at the substation. And that information gets published to the bus very quickly with very little latency. The local controller will be able to read that. It will then compare that value to what it measures locally with its local micro PMU, and then communicate to the devices, to the actuators. This basic schema scales up, and you can add essentially arbitrary numbers of devices here. In practice, you may want to keep it more local. You can add analytics at each local controller. In principle, you could embed all of this local controller, which runs on essentially Raspberry Pi or a small laptop, and the micro PMU capability. In principle, you could incorporate into an inverter here. The supervisory controller subscribes to whatever data are useful for it, which might include economic information, forecasts, and so forth. And then in our instantiation here, we also used PingThing's predictive grid for streaming the data to and archiving and doing analytics on the data so that we would be able to report on what all happened. And then again, there's functionalities that can be implemented here on predictive grid for anomaly detection, for analytics. So this is really a proof of concept for a secure communication data infrastructure that allows for different parties to share information without, overstepping boundaries. People, individual actors, get to see as much as they need to see about what's happening on the grid so that they can be good citizens and respond appropriately. And they don't need to see more than that. So some sample test results, those, it's hard to sort of intuitively see what's happening here without having the circuit model to compare to, or really having dived into the dynamics. But what we're looking at with these graphs are phase magnitudes, phasor voltage magnitudes and angles on the three phases A, B, and C. And we have a red line that's a target. And then we have these disturbances, which we've created artificially. We've created insanely big disturbances, loads, just improbably large step changes, turning on and off to basically stress out our phasor-based control system to see, can it respond? Can it coordinate the kilowatts from these actuators without creating any kind of instability or oscillation or disagreement between and among them. And so what we're seeing here, using the proportional integral controller with a time step of, I think, half a second here, it takes a couple of time steps to reject these disturbances, but we do come back to we settle back on the desired target values. When we use the linear quadratic regulator, the MIMO controller, it goes much faster. And recall that this is the one that has the benefit of having a really good distribution circuit model. And so it already knows how much P and Q from the actuators it should need in order to achieve a certain change in voltage, magnitude, and angle. And so essentially within a single time step, that thing just drives the condition at the performance node back to the target. It's pretty spectacular performance. Now those were on the IEEE 13 node feeder. We also did simulations on bigger, more complex, more realistic feeders with hundreds and hundreds of nodes and a lot of volatility in the loads and also a fair bit of phase imbalance. And essentially, it still works. We have, some amount of jitter here, but it's keeping the voltage magnitudes and angles within a pretty narrow band. If you can read the scale here, the target was set at 0.98 per unit, or 98% of nominal. One increment on the vertical axis is 0.02 per unit. So it's keeping it within a pretty tight range. And certainly from the standpoint of safety and tolerance, this would be very well within bounds. Now, you may wonder what happens if the supervisory controller issues targets that are physically infeasible for the actuators to respond to. And the answer is, well, they talk to each other and negotiate a little bit. So in this example, we have disturbances that are being rejected. The target value is this yellow line. And then the supervisory controller makes a really radical jump, which in real life we wouldn't want it to do that, but this is for stress testing, the whole control setup. So it says, well, instead of 0.99 per unit, I want you to go bring the voltage down to 0.92, which is this green line. So again, not really realistic, but what we have here for the actuators are some batteries, which when they see that, well, wait a minute, our voltage phasor was here at 0.99 per unit magnitude, and now we're supposed to get it down to 0.92. That means we need to increase load. We need to charge up the battery as much as we can. That wasn't possible on all three phases, so we got close here on phase B, but on phase A and C, couldn't quite get there. So that's when the local controller sends back an I can't do it signal to the supervisory controller to say, hey, we're trying, we're doing our best, we're driving the system as far as we can in the direction that you told us to, because that's presumably where we're going to be safe and steady, but we can't get there, so please recalculate the target and give us something more realistic. So the supervisory controller responds with this compromise, and that's the red line as a new target. And what we're showing here is that back and forth communication after a few time steps is successful, and the battery now is able to maintain, not quite exactly on B phase here, but more closely on the three phases, because it's a very unbalanced situation, but it's able to drive the system to that new target. Certainly, a vulnerability is a loss of communications, and so we've tested what happens when stuff drops out. Basically, we have to fail safe to revert back to a strictly local control. But what's noteworthy about the phasor-based control is that really there's only one remote stream of data that you need, and that's from the reference PMU. The reference phasor is the only non-local bit of information that you need in order to maintain the system and maintain the last published phasor target. So that's a comparatively low amount of information that has to be transferred on an ongoing basis. Some of the biggest challenges that we anticipated here, first of all, is the fact that we require this very precise measurement of a small number. Voltage phase differences, especially in distribution, are small numbers, And they correspond to large power flows in the tens or hundreds of kilowatts. So it's not a nicely conditioned problem, but it's workable. And there are, in fact, many realistic resources, in particular commercial industrial loads, aggregations of EV chargers, for example, and larger solar PV inverters that really can make a noticeable difference and have a real impact on distribution circuits, and then additively translate that impact up toward the transmission system. So we've shown that it's essentially feasible to work with those numbers. We've also worked with the supervisory control optimization to see how we can trade off speed versus accuracy in a linearization of the optimal power flow problem. That can take a long time to compute if you do it very accurately and very carefully, depending on how large a system you're dealing with. So we actually developed some techniques for taking appropriate shortcuts, including a loss approximation power flow, and an iterative procedure for essentially arriving at the solution that will give us close enough to the operating state that we're looking for in a reasonable amount of time. I already spoke about the alternative controllers, local controllers. Depending on whether we have a good network model or not, we can choose either type of controller. The really important thing to note here too is that phasor-based control does not inherently require that all the local controllers are the same. So you could be using different algorithms, different makes and models in different places. Finally, scaling should work. In simulation, there's no reason to think that we would run into any showstoppers if we work with bigger circuits, bigger networks. Really the main issue, the main challenge that we haven't addressed is having explicit real and reactive power control when talking to inverters, because inverter manufacturers, are a little protective of what's under the hood there and don't necessarily want their devices to be responding to all kinds of different inputs externally. It's more typical to have, say, real power control with a power factor setting or something sort of higher level. So that actually posed an issue for us just in terms of the time step, because we couldn't get inverters to respond to our signal as rapidly on as short a time step as we might have liked. That's not a basic physics limitation. That's just a limitation of who has access to what level of control loop. And to me, it makes a lot of sense to just embed this whole phasor-based controller inside the inverter. So in conclusion, we've shown that phasor-based control can work. We've shown that we can track voltage phasor targets very closely to within 0.5%, which seems plausible in terms of real-world operations. We can reject very, very large disturbances. And we think that phasor-based control can really manage utility, help manage diverse resources for utility, or it could be a third-party aggregator who's coordinating resources. We think the paradigm is robust to failures, and we're confident enough now that we would like to try this in the field. So stay tuned for that. Meanwhile, I will leave you with some reading. Enjoy.